Okay, let's get started. Just a few housekeeping notes before we jump back into lecture. You're working your way through deliverable 4. How many people have started on deliverable 4? Good. How many people have successfully imported scikit-learn? Most people. Anyone having problems installing scikit-learn? None. All right. That's good to hear. Okay. It's the last library we're going to be importing and wrestling with in this course, so there you go. Okay, so let's carry on. We're working our way through our second theme on design, and we're going to finish our discussion today on designing visualizations today. We'll spend probably most of today finishing lecture 6 and sort of start in on lecture 7 today, where we'll start a 2-part series on the design process itself, right? So design philosophy is sort of your idea about how you want to translate a need or a want into a product or a service. Design principle is kind of a rule of thumb of things you want to keep in mind and try to do during the design process. So we'll talk more about the design process today and next week. Okay, so last week we were talking about visual design. And we were talking about visual design in the context of the data flood, right? The big data revolution that's upon us. How do we start to find structure in that data? Machine learning algorithms, like the KNN algorithm that you're working with this week, are able to find structure in data, but often a first step is to try and visualize that data and look for patterns yourself. So we started talking about that last time. We looked at a few examples. We talked about why visual design is so difficult. We often can't just simplify or systematize because we lose information. We've talked many times now in this course about visual metaphors. How do we go about doing that? And we ended last time by watching the TED Talk of Hans Rosling, where he was introducing or walking you through Gapminder, which is sort of this running example technology through this course. We didn't quite finish the TED Talk, so I think there's about 2 minutes left. We'll watch the last 2 minutes, and then we'll come back to these questions. What are the aspects of the visualization that Rosling drew our attention to, and how did they illustrate various aspects of health and wealth data over the last 10 years or so, and what are some of the metaphors that Rosling used during this talk? Okay. I think we got to about here. So about 5 minutes left, and I will turn up the volume for us.
Universal access to HIV for that quintile up here with the same strategy as down here. The improvement of the world must be highly contextualized, and it's not relevant to have it on regional level. We must be much more detailed. We find that students get very excited when they can use this. And even more policymakers and the corporate sectors would like to see how the world is changing. Now, why doesn't this take place? Why are we not using the data we have? We have data in the United Nations, in the national statistical agencies, and in universities and other non-governmental organizations, because the data is hidden down in the databases. And the public is there, and the internet is there, but we have still not used it effectively. All that information we saw changing in the world does not include publicly funded statistics. There are some web pages like this, but they take some nourishment down from the databases, but people put prices on them, stupid passwords and boring statistics. And this won't work. So what is needed? We have the databases. It's not a new database you need. We have wonderful design tools, and more are added up here. So we started a non-profit venture, which we called Linking Data to Design. We call it Gapminder, from London Underground, where they warn you, mind the gap. So we thought Gapminder was appropriate. And we started to write software which could link the data like this. And it wasn't that difficult. It took some person years, and we have produced animations. You can take a data set and put it there. We are liberating UN data. Some few UN organizations, some countries accept that their databases can go out on the world. But what we really need is, of course, a search function. A search function where we can copy the data up to a searchable format and get it out in the world. And what do we hear when we go around? I've done anthropology on the main statistical units. Everyone says it's impossible. This can't be done. Our information is so peculiar and detailed, so that cannot be searched as other can be searched. We cannot give the data free to the students, free to the entrepreneurs of the world. But this is what we would like to see, isn't it? The publicly funded data is down here, and we would like flowers to grow out on the net. And one of the crucial points is to make them searchable, and then people can use the different design tool to animate it there. And I have a pretty good news for you. I have a good news that the present new head of UN Statistics, he doesn't say it's impossible. He only says we can't do it. And that's a quite clever guy. Huh? So we can see a lot happening in data in the coming years. We will be able to look at income distributions in completely new ways. This is the income distribution of China, 1970. This is the income distribution of the United States, 1970. Almost no overlap. Almost no overlap. And what has happened? What has happened is this. That China is growing, it's not so equal any longer, and it's appearing here, overlooking the United States, almost like a ghost, isn't it? Huh? It's pretty scary. But I think it's very important to have all this information. We need really to see it. And instead of looking at this, I would like to end up by showing the internet users per 1,000. In this software, we access about 500 variables from all the countries quite easily. It takes some time to change for this, but on the axes, you can quite easily get any variable you would like to have. And the thing would be to get up the databases free, to get them searchable, and with a second click to get them into the graphic formats where you can instantly understand them. Now the statisticians doesn't like it because they say that this will not show the reality. We have to have statistical analytical methods. But this is hypothesis generating. I end now with a world there the internet are coming, the number of internet users are going up like this. This is the GDP per capita, and it's a new technology coming in, but in amazingly how well it fits to the economy of the countries. That's why the $100 computer will be so important. But it's a nice tendency. It is as if the world is flattening off, isn't it? These countries are lifting more than the economy. It will be very interesting to follow this over the year, as I would like you to be able to do with all the publicly funded data. Thank you very much.
Okay, so an interesting video and also a little bit of a historical document. This is from the mid-2000s, so things have changed quite a bit since then. What were some of the parts of the visualizations you saw here? How was Rosling using this to tell a story about health and wealth?
I really like the ability to see changes by using the slider to have it moved in actual time, visualize time over many years.
Absolutely. So the slider bar is sliding forward and backward in time, right? There's a bit of a metaphor there. He mentioned right at the end of this video this thing about statisticians not liking Gapminder because there's no good statistical analysis, there's no p-values associated with it, there's no confidence intervals. And Rosling said that's not the point. The point here is hypothesis generation. What did he mean by that?
Like if you're just trying to start a business or something, you can look at data over time and see where need would be.
Absolutely. So you can look at data over time and see where need may be. You might have a hypothesis or an idea about where need may be, and you might be able to see a pattern in the data. What else does he mean by hypothesis generation? Did you have an idea? Yes?
If you can easily see the correlation between two things, then you can generate a hypothesis about why there's correlation.
Exactly.
What is causing what.
That's it, right? So nothing in here says anything about cause and effect, right? The very famous phrase, correlation does not imply causation, right? So you can see throughout those 20 minutes lots of relationships between health and wealth, but the Gapminder data itself says nothing about why those relationships exist. But it might generate in your mind a hypothesis. You might generate an idea as to why there is a relationship. You might then take that hypothesis and dive back in the data again and plot different data to see whether that additional data you bring up in Gapminder or perhaps elsewhere supports or disproves your hypothesis. So in HCI, right, we can't forget the I, that interaction part. Most of the time, we're not just creating static images or even videos. We're creating a feedback loop, an interaction between, in this case, the observer and some interactive visualization system. And what is the need or the desire of the user during that interaction, right? Remember the P, impact analysis. What is the user trying to do? Well, they might start by playing around with Gapminder. They may have no specific goal in mind. They're just sort of playing around and moving the slider bars and starting to understand how this system works. Then they might start to notice patterns, relationships between health and wealth. Then they might formulate a new goal or a new hypothesis, which is, I wonder if this relationship is being caused by ... They may dive back into the data and go looking for those hypotheses. Okay, let's step back to correlations. What are some of the patterns that exist between health and wealth in this video, and how were those relationships made clear using different visualizations in Gapminder?
Well, very simply, he just plotted, the death rate or the birth rate versus GDP or some other metric.
Exactly, right? So the most common one that you see here is a scatter plot, right? Vertical axis is one indicator, horizontal axis is another, and if they sort of line up along the diagonal, then there's a relationship between these, a correlation. That's pretty common, but he showed some other visualizations and some other metaphors associated with those visualizations. What were they? What else did you see besides just the scatter plot?
You have the graphs that were kind of like layered.
Exactly, right? You remember the one with these blobs that were falling on top of one another? What were those visualizations? What were those blobs? Wealth distribution, right? So it's a distribution. You can think of it as a density distribution, right? So the horizontal axis was wealth, GDP, how much people make per year, and then the height on any point in the blob is the fraction of people that make that amount of money per year, right? So we're looking at these density distributions, and they were being layered, they were being dropped on top of one another. Why? That was an animation, right? So what was the metaphor associated with dropping these density distributions on top of one another?
To show overlap.
To show overlap, right? And also to show cumulation, right? So you can see a distribution within a particular region of the world, but as you dropped more and more of the regions on top of one another, a picture started to emerge. What was that overall picture?
Was it the global distribution of like yearly or daily income?
Global distribution of wealth, right? On average, how much different people on the planet make per year, right? And he was trying to explode a common misconception, which is there are the poor people and the rich people, right? And if that were true, what would you expect to see for the global distribution, given this visualization? You'd see a bimodal distribution, right? You'd see a hump that includes most of the poor people on the planet and the other hump at the right edge of the plot that would show all the rich people, but that was not the picture that emerged. What was the picture that emerged and what was the point? He said it quite a few times in different ways throughout the video.
We only saw one hump, and that means that most people are in the middle.
There's one hump, right? Most people in the middle, but it also doesn't, it wasn't a spike, right? So it was pretty spread out. So there's everything, as of 2004, there was everything on the planet, right? There is no us and them in terms of wealth. There's everything you can imagine, right? At the global level. Then he had these bubbles, and he had a different visualization where he would burst the bubble. This was a question on the quiz, so this should be fresh in your mind. What was the metaphor there?
It's not necessarily good to break it down by region, because within regions there's dramatically different countries, cultures.
Absolutely. So globally there is everything under the sun. I think he used that phrase in terms of wealth, right? And same thing for regions and same thing for countries, right? So he had a bubble, which was a region, and he popped it, and then you'd have different countries in sub-Saharan Africa, where now every bubble was an individual country, and then he popped some of those individual country bubbles, and they also spread out horizontally, showing the five quintiles, the fifths of wealth distribution. Why did he pick that particular visualization of popping bubbles? What was the metaphor that was carrying the message?
It's like breaking a big thing into its smaller components.
It's breaking a big thing into its smaller components. That's one half of the metaphor, but a metaphor says breaking bubbles is like...
It's breaking our expectations.
Absolutely, right? Bursting your preconceptions or breaking your, misconceptions about the idea, right? He didn't explicitly say that, but that's what was meant, right? If you average things, you often get an unclear picture about what's going on. So as you dive down into the data, things start to look very different, right? Okay. It's a good exercise to go back and watch that video at your leisure and look at all these metaphors. I think if you're interested in doing interactive visual design, Gapminder and Rosling's presentations about it are a great source of inspiration. He ended the lecture by talking about data liberation, right? There is all this data out there, but it's hard to get at it. That was a video, this talk was made 14 years ago. What's the situation like today?
I venture to say that most data is easily accessible. Like he wanted to be searchable, and you could do that on Wikipedia and have sources to back it up, or there's like a lot of UN sites.
Okay, so search it is much easier than it was 14 years ago. But searching for and accessing data...
I would say that it really just depends on the data.
Depends on the data. You can play this game by going to Google and type in, give me the last 10 years of GDP data for the United States. And you might get back a PDF. If you're lucky, you might get back a spreadsheet, maybe. Still not so easy, right? There are data repositories out there. It's getting easier, but still a little bit of a challenge to easily access the data, easily visualize it yourself. You still need to do a little bit of hunting, and it definitely depends on the data source, right? For those of you that are taking Professor Bagro's data science course, I think you look at a lot of different data sets in that course. Some of them are easier to find than others. So a big challenge in the big data era is still being able to get at that data. Wouldn't it be great to download a data set and pull it into NumPy and just plot it very easily? Some cases it is easy, some cases not so easy. Okay, let's move on. I forgot to bring my Tufte book today, but if you're interested, I highly recommend finding or borrowing a copy of The Visual Display of Quantitative Information. This book, written back in 1983, became sort of the Bible of visual design, and there's been a lot of follow-up books by Tufte and by others. And we're going to structure the rest of this lecture around three of Tufte's most famous books. The first one, which he described as pictures of numbers. So these are numbers or data about things which may or may not have a physical counterpart in the real world. So Gapminder, which we just saw, was visualizations of numbers about intangible things. GDP, health metrics, wealth metrics, concepts, right? Relationships between concepts. How do we bring to life relationships between abstract concepts? We're going to look at a few examples of that in a moment. His follow-up book, Envisioning Information, which was the reading last week, he described as pictures of nouns, or things that actually do exist in the world. This is mostly a book about maps. So we have physical objects out here in the world. They have physical relationships to each other. This building is closer to that building than it is to another building. If we create a map of campus, what is the best way to create such a map? We'll talk about maps in a moment, and we're going to end this lecture by talking about his third book, which was Pictures of Verbs. So verbs, in this case, was shorthand for things that change over time. If we want to visualize things that change over time, one of the easiest things we could do is make a video, something that also changes over time. But there's a drawback to videos. You remember our discussion about chunky and streamy data? What's the challenge with video?
They're streaming.
Sorry?
They're streaming.
They're streamy, but what's the problem with, or what's the drawback to streamy approaches to visualization?
So you can focus on a video really easily, but it's hard to like really absorb and remember everything you see.
It's hard to absorb and remember. It's very attractive, engaging, right? It's very hard to look away from something that's moving. However, you tend to forget, right? So a lot of what we want to do is try and leave the observer with information or hypotheses. So could we create a static image, or what's the best way to create a static image of a phenomenon that's changing over time? Just for fun, he also wrote a book about the evils of PowerPoint. I'm not using PowerPoint, so I guess I'm okay. It's an interesting book, which is about basically his overall theme, which is the way you present information influences the way you think about information. Seems kind of obvious, right? But if you think about PowerPoint and any kind of slideshow presentation, which is the normal way we tend to communicate information when we're presenting to an audience these days, it's deeply hierarchical, right? You're looking at an individual slide now. This slide is part of a slide deck. That slide deck is part of a set that is part of the second theme for this course, and this course is made up of 6 themes. There are good reasons to have a hierarchical organization, but it also enforces ways to sort of think sequentially. I forget the name of it now, but there was another presentation app a few years back that tried to get away from this idea of presenting information sequentially. Does anybody remember what it was? Prezi. Does anybody use Prezi anymore? I don't know. It was a good attempt, right? But somehow didn't quite catch on. But it was an attempt to militate against this sort of lockstep sequential presentation of information. Interesting book to read if you're interested in the relationship between how we present information and how it influences our thinking. Okay. Let's start with pictures of numbers, and the obvious thing here again is to create graphs. And we've seen a lot of those so far: scatter plots, cumulative density distributions, animations, and so on. So often one of the most effective ways to describe, explore, and summarize a large amount of data is to look at pictures of those numbers. But looking is a passive process. So remember that usually in HCI we're trying to do something interactive, where the person comes to the visualization with a particular goal or activity in mind, and we want them to be able to use the graphics as an instrument for reasoning about quantitative information, right? I see a correlation in the data. I wonder what's causing that correlation. Can I change the visualization or pull another data set into the visualization to prove or disprove my hypothesis? And we'll see some examples of that in a little bit. Okay. So this book is great because it presents a lot of different ways of graphing information. One of the challenges about graphing information is usually you have a lot of information, and we need to find a way to collapse that data down into a digestible format. As Rosling mentioned in his TED Talk, they have about 500 health and wealth indicators that they could plot. But unfortunately, humans cannot see in 500-dimensional space. So we can only look at the relationship between relationship between 2 indicators at a time, right? So in this case, population and carbon dioxide emissions. Or can we? How would you expand a scatter plot to see relationships between more than 2 health and wealth indicators? What are some strategies you might employ?
You could do some sort of shading or visual on the dots.
Okay. Absolutely. We could try and we could sort of simulate a third dimension, perhaps depth or opacity. We could try and add something else. Of course, there aren't just two variables that are being plotted here, right? There are actually four. Population, carbon dioxide, population inside of the countries, which is the size of the dots, and the color of the dots indicates which region, which part of the world that country is a part of. Right? This is a rug plot described in the book, which again is going to assume we want to see things in 2 dimensions. And in a rug plot, you create 2-dimensional scatter plots, multiple scatter plots, and then line them up so that neighboring plots, like the top 2 you see here, if you have 2 horizontal neighbors, then their vertical axis should be the same. So it might be a little bit hard to see in the back, but in these 2 plots here, they share the same vertical axis, which is child mortality per 1,000 children born. If we have 2 vertical neighbors, then we line them up so that their horizontal axes are the same, which in this case is GNP, gross national product. And then how do we read a rug plot? Well, in this case, I picked out 2 countries, China and the United States, and connected them by lines. So we can now compare how many health and wealth indicators between China and the US in this picture. We'll forget population and region for a moment.
Great.
We've got carbon dioxide here, 1, 2, which is child mortality, 3, which is GNP, and a 4th one, which is life expectancy. So there's 4 health and wealth indicators that visually you can compare for China and the US in this picture. It's a little bit more effort than it is here. Why? Why is it a little bit more effortful here to reason about the relationship between these 4 variables between these 2 countries?
Well, first of all, you expect more from the person interacting with the graph.
Absolutely. So we're interacting now in just the sense of jumping around the visualization, right? But it definitely is a little bit more challenging. Why?
You have to hold more in your mind at one time to make a connection.
Absolutely. You have to hold more in your mind, right? So this is not unlike the Spot the Difference cartoon game we were playing last week, right? You got to hold that in your mind. But if you do, you can reason about the fact that the US is a bigger polluter, more safe in terms of child mortality, richer, and healthier in terms of life expectancy, at least in the year 2004 and 2002. Okay, so again, the observer has to do a little bit more work, but even staying in 2 dimensions, we can reason about more and more variables. We can add more and more plots here. It gets a little bit more challenging. You'll notice that I've also put this cross-hatching at the intersections between them, which are 1-dimensional projections, right? So what we're looking at here is, again, a density distribution for GNP, which is our horizontal axis here, and each line here corresponds to one of the major countries in the plot. What are those 1-dimensional projections telling us? It's some additional information we're presenting.
Just clusters of information, like what countries produce like the most, or have the best GDP, or produce the most carbon dioxide.
Exactly, right? So this is sort of a cheap version of these blobs that you saw in Gapminder, right? Density distributions. We've got this gap between the pair of plots, you might as well use it, right? So there's a fair bit of ink here. There's a fair bit of things going on in this visualization, but we're trying to present a lot of information. So this first book by Tuft is, again, lots of different strategies or design principles, if you like, about how to maximize the data to ink ratio. You may or may not be a fan of rug plots, but the nice thing about this book is the wealth of different ways that you can do this without relying on going to a 3rd dimension or an animation. What can we do simply in two dimensions? Okay, here's another interesting one. Way back in 2008, there was the financial recession. How would we plot that information? So we're going to focus now on just just economic data. Any ideas? It's a common way of presenting economic data. The ticker tape, right? Up and down of profit and loss. Here's a different way, which has some interesting properties. This is the plot of the global economy back in 2006 and 2007. And I've got a link now to the website, and I'll show you the recent version of this visualization. This is what things looked like over the year leading up to the financial recession. The first time I taught this course was the spring of 2007, so this was going on when I first taught this course. Note the dates here, March 2nd, 2006 to 2007, and on the next day, this is what the global economy looked like on March 2nd, 2007. We're going to play the same game here that we played when we first looked at Gapminder. I'm not going to tell you anything else about this visualization. You tell me. What are some of the strategies in this visualization, and what information is being conveyed using those strategies?
A lighter shade of green means more activity.
A lighter shade of green means more activity. Close, not quite.
I'd say a lighter shade of green means healthier of an industry.
Healthier, right? So green here is going to be profit, and red is going to be loss. And the color map is going to go from light red, darker red to black, meaning no profit or loss, from black up to lighter and lighter shades of green. If you, in your final project, when you start to play around with Matplotlib comes with a lot of color maps, which means a spectrum of colors that you can use for different things. A common color map, as you can imagine, the most popular color map in Matplotlib is green shading into red, because most visualizations are trying to show bad versus good in some form, right? So for us now, red is going to be economic bad, and green is economic good.
Do the squares or rectangles represent individual companies?
Do the squares represent individual countries? What makes companies? What makes you think that?
Well, the fact that they're different sizes, not labeled.
Yep.
That, and that they're broken into sectors.
They're broken into sectors, right? So you've already inferred that there are sectors here. And again, they're cheating a little bit because they've written the sectors on here. So most people can usually figure out that the bigger rectangles represent sectors of the economy, and individual rectangles inside the bigger rectangles represent individual companies. Correct. Some of the rectangles are bigger or smaller than others. What do you think that what does that represent? Another visual metaphor.
The impact they have on the economy.
The impact, can we be a little bit more specific?
Market share.
Market share or market volume, right? If this was a perfect metaphor, we'd be looking at it in 3 dimensions, and literal volume would represent market volume, right? Exactly that. So market share is size, and economic health over a particular time period, average health over that period is represented. This was taken in 2006 and 2007. Anyone want to hazard a guess as to what any of these individual rectangles actually are? Which companies are being shown here? This is also a historical exercise by now. Twitter didn't exist at that time, so don't guess Twitter.
Microsoft?
Where's Microsoft on here?
Could it be the? I can't tell if there's multiple black ones right there, but it'll be probably the biggest one in the technology.
I think it is. I think you're right. I think it's this one, or Apple, something like that. What do the small n's represent? This one's a little bit more difficult.
It seems like they're all, almost all of them relatively small, so it could be new companies, like new companies in that.
It's a good guess. They're news stories that were reported about those companies during that period. It's a little unintuitive. All right, let's have a look at today's version of this. I didn't want to show you this one because obviously you can kind of guess from the acronyms what things are. Okay, so very different picture compared to before. I'm not sure why it's not showing color here. Oh, there we go. Okay, so over the last week, Amazon has dropped by 3% of market share. Google stayed about even. Microsoft stayed about even. There's Apple down there. So we now have, for the first time as of 2 or 3 weeks ago, the first trillion-dollar companies, right? There they are, Amazon and Apple, the big rectangles. Okay, let's step back from the fact that this is plotting economic data. Why plot this data in this particular way? This is not a scatter plot, it's very different. Why this very different visualization for this data?
Well, there's a lot of things that affect our economy, so being able to block it out into these big sectors allow you to focus on something you're interested in.
Okay, you should block it out into these big sectors, right? This sounds very familiar to something we've been talking about several times so far, which is hierarchy, right? We have 3 levels of hierarchy here. We have the global economy. You can imagine creating an animation where the entire rectangle gets bigger or smaller over time, representing the growth or shrinking of the global economy. At the next level down in the hierarchy, you have the overall sectors of the economy, and the size of those big rectangles matters. That's the share, or the fraction of market share for all the financial companies, technology companies, and so on. And then the next level down, the third level in the hierarchy, are the individual companies, and we can see things about those individual countries. So often we want to represent data in a hierarchical manner, and a tree map is a common way to do this. There's an app where you can visualize what's on your hard disk, and it'll do the same thing. The overall rectangle is your entire hard drive. Individual rectangles are individual files. What do you think the middle level of the hierarchy represents? You've got your whole hard drive here, individual files at the lowest level of the hierarchy. What's the middle level? What's the equivalent of sectors of the economy?
The different folders right on the drive.
In some cases, it's folders. On other apps, it's the file type, so it'll group all your videos together, all your photos, all your apps, all your cache data, and so on, right? So 2 very different data sets, but both have hierarchical organization and a good way to present information. For those of you that work in this kind of area, keep tree maps in mind. They're a great tool. Okay. Okay, let's move on now. We could spend the whole course talking about various kinds of graphs. The takeaway message here for today is think about the kind of data you have on your hands and think about what people want to do or take away from that data, and that should influence the T, impact analysis, which in this case, the technology is simply what kind of visualization might be appropriate for the data and what people want to do with it. Okay, let's talk about creating visualizations to represent many nouns lying on the ground. We've got stuff out there in the world, and we want to create a virtual representation of it. So any map or network visualization is always going to have some form of correspondence between the actual spatial organization out there in the world and the same spatial orientation in the visualization, and that correspondence doesn't necessarily have to be perfect. No matter how accurate a map of the real world is, it's always warping this relationship. What's the most important way that spatial organization out in the real world is transformed into spatial organization in a map? It's shrunk down, right? You usually don't have a map which is to scale. It's not going to be very helpful, right? Seems obvious, but keep that in mind, right? That is one of many abuses of this correspondence that are often built into a map for good reason, because you need to think about what people are going to do with it. If they're going to hold it and walk around, or at least look at it these days on their phone, it's not going to be life-size, right? Okay. This is the lecture in which we're going to visit the London Underground twice. We heard about it the first time in Hans Rosling's talk. If you go to London, you take the Underground, you step off the platform into the tube, you'll hear the announcement, mind the gap between the two. That's where Gapminder comes from. Here's a visualization of the London Underground. And again, I apologize to those of you in the back. This is going to be a little bit challenging. But I want you to try and find the best route between Borough Station, that's circled in red, and Warwick Avenue, which is circled in purple. And by best, I mean the route in which you have to switch trains as few times as possible. Go ahead. Should I make this a little bigger? Actually, let's... Has anybody found the best route yet? They think they found the best route? How long did it take you? Okay. All right, let's play exactly the same game again, but using the actual map of the London Underground. Better, right? Much, much better. What's the best route here? Sorry?
Take the mountain train.
Should we start from Borough Station? Go down to Elephant and Castle on the black line, northern line. Yep, and then. All right. Yes, correct. Very good. Okay. Most people, it's much easier using this map. It's much better, right? What is the A here in pact analysis? The activity of most people using the underground is how do I get from A to B as quickly as possible or using as few changeovers as possible. How does this map help with that?
Puts all the lines on horizontal verticals.
Absolutely, right? So there's many simplifications on this map. There's been whole books written about this one visualization, probably the most famous visualization of all time. One simplification is only vertical, horizontal, and diagonal lines because it hurts your brain to think about squiggly lines, right? So we'll talk about the visual system in humans a little bit later, simplify things, right?
You take away all the noise of like the actual city and streets and buildings.
Exactly, right? There is a huge amount of data here. I don't need to know where the Serpentine is and the fact that there's a small little ornamental island in the middle of the Serpentine Pond as I'm trying to get from Borough to Warwick Avenue. It doesn't matter. So erase all extraneous information. Another extremely important design principle, right? When you create a visualization, there is always a temptation to add stuff because you have it, right? You have access to Google Maps. You're creating a mapping application. Why don't we just throw up all the data we can get from Google Maps? Maybe yes, maybe no. What other simplifications are made here?
All the stations are on the same grid. They line up.
They all line up, right? If you look carefully, neighboring stations are not exactly the same distance apart, but more or less. What else?
Forgoes actual geography to show more so just the general idea of where the line is going.
The general idea of where the line is going. So there are a huge number of simplifications and geometric transformations that have been performed in this visualization, which means that in some cases there are stations here which on the map look very far apart, but you can actually walk between them in about 2 minutes above ground, and vice versa. There are stations here which are very close to one another in the visualization, but very far apart from one another geographically. So that seems kind of disconcerting, right? This is sort of a false map. The relationship between the actual physical locations of these stations and where they are on this map is very different. Why did they abandon that rule?
The most important thing with a map like this is like figuring out how someone has to be able to figure out how to get from point A to point B, and that's really like all that matters.
Exactly. The distance between A and B, generally speaking, doesn't matter too much, right? When you're taking a subway, distance doesn't matter. It's usually the number of exchanges you need to make, other information, right? If you're driving, that may not be the case, right? Now distance might matter. So the designers of this visualization thought carefully about what matters and what doesn't matter to riders on the London Underground. What other information is provided here as a nod to what people need to know when traveling on the Underground?
They have little circles where you can transfer.
Little circles where you can transfer, right? That matters. Yeah. What else?
And all the station names are there, but they're made like really small, so that that's not the focus, but you can find them like if you need them.
Exactly. Yeah, they're kind of backgrounded a little bit. What else? There's some additional information that's on here that wasn't on the other map.
Oh.
Sorry, go ahead.
It's on the other map, but
Yep.
each different train line is color coded, so you know when to stop.
Absolutely. Yeah.
Give you the zoning information.
The zoning information, right? So if you've ever traveled on the London Underground, or you do, you generally want to try and stay in Zone 1. If you go further out, or you're commuting from further out in, you pay more, right? So that matters. If you're trying to figure out how to get around in London, you're often asking yourself, can I get around in London using the Underground and stay in Zone 1, right? That's important. Again, a very specific detail of this specific activity, but it matters. Okay, let's move on. Let's move on to Tufte's third book, which was Pictures of Verbs. So now we're going to try and represent things that change over time. And again, we could represent them with a video, but let's try and do this with a static image, so that if there are relationships between variables in something that changes over time, we might be able to see them and remember them. Okay. How do we go about conveying motion and change in an unchanging image? Before we look at a few examples, what are some general ideas about that? How do you represent change over time in a static image?
I mean, you can have time as an axis.
Right, so you've probably seen scatter plots or lots of visualizations where the horizontal axis is t. Where is earlier and where is later on a horizontal axis for time? Seems like kind of a ridiculously obvious question. It's obviously always left to right, right? Left is earlier and right is later. It's obvious. Could you imagine a map where later was at the left and earlier was at the right? It'd be ridiculous. Why is it like that? Why does time flow from left to right?
That's the direction we read in.
That's the way in which we as English readers or speakers of the Romance languages tend to read, right? We read from left to right, so the words that are to the right, you're going to read them later in time than the words you read to the left, right? It's so obvious you probably never thought about it again, but we need to try and make some of those obvious assumptions explicit in case we need to change them or use them in a new visualization. Okay. Okay, let's have a look at another example. This is a little video from an experiment. An experiment I worked on a few years ago. Not very complicated here. We've got a little bit of a pendulum. And inside the base of this pendulum is actually just one sensor, which is sensing the angle of the arm relative to the base. So in my little cartoon here, the sensor is recording that the arm is 30 degrees to the right of vertical. And as the arm starts to move from 0 to 1 second, that angle decreases as the arm is swinging down. If we take the difference between the angle at different times, then we get the change in angle as a function of time, and let's just deal with degrees per second. So we're plotting in the bottom two plots here, angular velocity. So what is the velocity, the change in angle of the arm relative to the base? Okay, so what we want to do now is plot two variables, which is angle and angular velocity. And we want to see how both of those variables change over time. If we look at the top two plots here, it's pretty obvious that as the arm is coming down, it's going from 30 degrees to 10, then it's going to reach 0, then it's going to go to -10, then it's going to swing up to -30, and probably reverse direction, and so on. As the arm is falling, in the bottom two plots here, we can see that angular velocity is increasing, right? Gravity is pulling the arm down and it's speeding up. So that variable is increasing at the same time that angle is decreasing. We could again, as mentioned, we could plot time on the horizontal axis here, and because we have two variables, we're going to have two plots, this one for angle, this one for angular velocity, and if you look carefully, you can see that these variables are oscillating, which is what you would expect, right? You saw the video of the pendulum, but there are many things in that video that are hard to see because it's streamy that become obvious the moment you plot them, and we're looking at it statically. So what can you see in this picture that you couldn't see very well in the video, unless you're an expert in pendula?
The angle slowly gets smaller.
The angle slowly gets smaller so that we can see that, and again, hypothesis generation. That should suggest a hypothesis. Why do you think the angle is getting smaller over time? Any mechanical engineers here?
Friction.
Friction, right? So there's always friction at the base of the arm, and friction is taking energy out of the system. So eventually this thing will come to a stop. When will it come to a stop? When will this particular pendulum stop moving?
When the angular velocity reaches 0?
When it reaches 0, when will that be? This picture should help you think about that.
Never.
Not never, because we got a physical, it's a good guess. Not never, because we're dealing with a physical device. It will eventually come to rest. But you're right, it's going to take a long, long time to do that. The angle, or the height of the pendulum, is becoming less and less over time, but the rate at which it's becoming less and less is becoming less and less over time. You're going to learn more about pendula than you ever wanted to know over the next few minutes. Why is the angle becoming less, the rate of the angle becoming less?
When it's moving faster, the drag has a greater effect, but the friction stays the same.
Okay.
As it slows down, the drag goes.
Okay, that's right. So there are actually two things going on here, which is friction, but also drag. So there's a little bit of wind resistance. There's some other things that are going on, which as the pendulum swings less up and less down, those forces which are acting against the swing themselves become less, which means there's less resistance to the movement of the pendulum, so it will decrease at a decreasing rate. These things are very difficult to see if you go back and watch the video 10 times, 100 times, very hard to see. What about this one? This is angular velocity. What's happening here? This is degrees per second.
When the angle is at its maximum, the angular velocity is at 0 and vice versa.
Exactly, yeah, exactly. If you look very carefully, you'll see that when the angle is at 0, which is the sweep at the bottom of the swing, that's when angular velocity is highest, right? Which is what you would expect. There's a very high frequency here, so I needed to be very careful to line up these two panels exactly perfectly so you could actually see that. And angular velocity itself is decreasing over time. Kind of makes sense, right? So as the pendulum bar is swinging through a more narrow range, it's swinging slower, right? As this constricts, what this is telling us is that the pendulum itself is moving slower. As this constricts, it means that the range of motion is narrowing, right? And again, if you look carefully, the rate of angular velocity itself is decreasing over time, which means it's decelerating, right? So position, velocity, we could have plotted down here acceleration, but I think that's enough about pendula for now. Okay. Not quite. Got one more visualization for you. You can learn a lot from this. This is a pretty standard way of plotting change over time. But this simple way of visualizing things is weak in the sense that it doesn't always show you everything you want to know. In the same way that last time we were talking about the k-nearest neighbor algorithm, which is a weak learner, but it's simple to implement, right? A trade-off. The simpler the visualization, the more detail it hides. So let's look at exactly the same data, but I'm going to plot it in a different way. Has anybody seen this kind of visualization before? What is it called? Jack?
State diagram.
A state diagram or a phase diagram. How does this work? Well, you'll notice that there is no longer t on the horizontal axis. Now I'm plotting our two variables, angle and angular velocity, along the two axes. Where did time go? Time is now measured along this line. So let's go to time, at the beginning of time, let's go to 0 seconds. And at 0 seconds, as we see here, at that moment, the bar had a particular angle and a particular angular velocity. This is for the cartoon. In this case, at this particular moment, the bar had an angle of 160 degrees, which was up about here. This is 180 degrees. So the bar was at about here. And it had an angular velocity of non-zero, which means we pushed the bar. We started it moving. If we had rotated the bar to 160 degrees and then let go, this point would be at 160 and it would be at 0. Okay, so we raised the bar and then we pushed it. And then at the next second, if we follow along this line, as we move along this line, we're moving forward in time. The bar had a different angle and a different angular velocity, right? Okay, so around and around it goes. What can you tell me about the pendulum that you can see in this picture that's missing from this picture?
It looks like it's catching on something a little bit.
Absolutely, right? So the minute we made this plot, you can immediately see that at this particular angle, right, this vertical line, there's a bit of a hitch going on. It turns out that inside the base of the bar, there's a little metal rod which is rotating, and there's a sensor which is looking at that rotating bar and recording little ticks on the bar, which is how it infers angle. There was a little microscopic gouge in the metal of the bar that lined up with the sensor whenever the bar was rotated to minus 48 degrees, right? An incredibly minor detail, but it jumps out at you the moment you see this plot. It's here, it's plotted here, you just can't see it, right? So the way you visualize data matters, right? What else can you see in here that you couldn't see in the other ones?
You can see a direct, like, the direct relationship between angle and angular velocity.
You can see the direct relationship, okay?
I have a hard time describing this, but
Yep.
it seems to be like more horizontal at the beginning
Yep.
and more vertical at the center.
So exactly, so you see there these sort of bulges on the outside, and then as we move inside, as the angle and angular velocity are both approaching 0, we get a cleaner and cleaner oval, right? The reason for that, we need to get into the aerodynamics of wind resistance and all sorts of other things. So there's some even more complicated, subtle details that are going on. Even if we don't know what they are, we know they're there, right? Again, you can see it here, can't see it here. Okay, I don't expect you to remember all these details about pendula. The point is, choose your visualization carefully. Okay, as I mentioned, this was drawn from a research project I worked on a number of years ago, and just for fun, we created this visualization, and I'll just walk you through what this is. We're looking now at 12 phase diagrams, just like the one we just saw. In each one, the horizontal axis is angle, and the vertical axis is angular velocity. I've color-coded it now, where warm colors, which are easier to see here, represent points in time in which the pendulum spent more time there. So it's a little difficult to see, but this hot area here is near 0, 0, which represents the pendulum spent quite a bit of time at very slow speeds and towards the bottom of the swing. Here's the phase diagram created from the actual data. And in this case, we were doing an experiment where we created a machine learning algorithm, and we're not going to go into the details of that algorithm. But instead of the KNN algorithm, which is looking for neighbors, what this algorithm is doing is taking as input data, in this case the real data from the pendulum, and translating that data into its best guess about how angle changes over time. So you'll have to remember your calculus for a moment. It's trying to come up with a description of how angle changes over time and how angular momentum changes over time. Right? So we were just kind of playing this game ourselves. We have the data, and we were trying to reason or come up with explanations for why we saw the values of angle and angular velocity that we saw. Here, the computer is giving us back mathematical equations, and it says, this is what I think is going on. The angle is changing over time as W here for our purposes, which is angular velocity. Is the computer correct in this case? The computer is telling us, I think that the best way to represent mathematically the fact that angle is changing over time is to use this W thing that you've given me, which is the second variable. I don't know what W is, but it definitely seems to represent how angle is changing over time. Is the computer right? W here is actually angular velocity, how angle is changing over time. I see some of you shaking your heads, and you may be shaking your heads because this picture does not look like this picture. Okay? It turns out that in this case, the computer was right about this part of the equation. The computer has discovered that W, and it doesn't know that W is actually angular velocity. It actually figures out that it is. It says W is angle changing over time. It got that part right. Then it's trying to tell us how angular velocity is changing over time. In this case, it was wrong. It came up with the wrong guess, which, again, unless you're an expert in mechanics, you might not know that that's the wrong guess. So how can we visualize how right or wrong the computer is? The way we do that is over here, we took actual angle and angular velocity from the pendulum and drew the phase diagram. The computer then made 11 guesses. Each one of these plots has its own pair of differential equations. The mathematics of how the computer is guessing what's going on. And we take that math, which is very hard to read for most people, including myself. It's hard to read. We take that math, we plug in an initial value for theta, an initial value for angular velocity. That might give us a point here. And then we start to integrate these differential equations, which will trace a line through this picture. Then we pick another value of angle and angular velocity, plug it in, and start to integrate these differential equations. That will draw another line on here, and another line, and another line, and another line. We then take all of those lines, and we create this visualization. Parts of this figure where lots of lines intersect. We put hot color and dark regions where few or no lines ever visit. Okay. By doing that, you can see at a glance how close or how poorly the computer is doing at discovering the equations that describe a pendulum. You can go and look up on Wikipedia what the actual equations are that describe a pendulum, and you can see how close these guesses actually are. Easier to look at the picture. Which of these 11 guesses were better than others?
I think the bottom left one is probably the best.
Absolutely. If you go and look at those actual equations, they're pretty close to the equations of an actual pendulum. Right? I think that's about it. We also like this because it produces lots of pretty pictures. When we published this paper, we submitted this to the editors and said, you should use this as the cover of the journal for this month. They said, no, maybe not. Tried to get the cover, didn't quite make it. Okay. We thought we were a shoo-in, but there you go. Okay. Okay, let's end with, again, pictures of verbs, things that change over time, and the hardest part, which is illustrating cause and effect. So let's go back to Gapminder for a moment. Just remember that we're looking at correlations here. Let's go back, in this case, to two different countries, Brazil and the Republic of Korea. And you'll notice in this picture that there are these two different trajectories. What do the difference between these trajectories tell you about these two countries? Should be pretty good at reading Gapminder graphs by now.
Korea reduced infant mortality a lot faster than Brazil.
Korea reduced child mortality faster than Korea. Rosling actually mentioned this rather quickly in the talk. Does anybody remember? So he mentioned you move much faster. There's a metaphor right there. You move much faster if you're healthy first rather than wealthy first. So the red line is moving faster than the yellow line, right? You can just see that. But the question then is why, right? Well, now we're trying to get into cause and effect. So Rosling actually should be a little careful here. He's making a statement, but it should be a question, right? It's a hypothesis. You see that, and you might ask why Korea moved faster than Brazil over this time period. One possible hypothesis is that it moved faster because it was healthier first. Korea started back in 1975 with a lower child mortality rate than Brazil. Brazil was actually wealthier than Korea at that time. The GNP in Brazil was higher than it was in Korea at that time. So Korea was wealthier, Brazil was wealthier first, but Korea was healthier first. Let's go with this hypothesis. We hypothesize that countries move much faster if they're healthy first rather than wealthy first.
So I'm just kind of confused. Isn't
Yep.
this graph kind of bad? Because Brazil definitely reduced it by a lot more. Just in general, it went from like 100 and like probably 20 to around 40.
That's a good
Where they went
catch.
from 30 to 5, which is very impressive. But I think Brazil had a lot more actual like improvement.
That's a very good catch, right? If you look here, the vertical axis, it's not quite logarithmic actually, I'm not sure. Oh, it is log, okay, never mind. So you're right, so in terms of absolute difference, Brazil actually made more improvement. And Rosling glossed over all these details, but Brazil was starting from a worse point. So if you have 100 children dying per 1,000, it is easier, not easy, but easier to implement health interventions to reduce that number than it is when you're already at only 30 deaths per 100. So the logarithmic scale is itself kind of a metaphor, which is that it's harder to move down when you start at a lower point on this graph. But a good catch. Okay, let's take this as our hypothesis, and let's interact, at least just mentally, with Gapminder here. We could actually bring up the website and do this. How might we dive back into how might we actually dive back into Gapminder and find additional data to try and prove and disprove our hypothesis? We don't know that starting healthy lets you move faster, but we could collect additional data to try and corroborate that.
Can we look at other countries?
Absolutely, right? So deselect Korea and Brazil, pick two other countries, and we have to pick those two countries in such a way that we have to pick two other countries that have a certain relationship between them. What is it? Can we just pick two countries at random? Does it matter?
One's healthier and less wealthy than the other.
So we want to try and pick one that has the same sort of relationship, right? Which is one has to be wealthier and the other one has to be healthier at the start, and then see if that holds up. Let's say we find a whole bunch of country pairs that have that relationship, and we see the same pattern. We see whichever one of the pair of countries is healthier first tends to move faster. Are we right?
You've really just reinforced your correlation. You haven't really proven any
So we'd have to go in and actually do something else aside from the data. We're collecting data that supports or maybe disproves our hypothesis about cause and effect, but you can never really know unless you go in and find the actual mechanism, the details. But we can find data that supports or disproves to some degree. Now, if we always pick a pair of countries in which one is healthier and the other one is wealthier, there's a second hypothesis, which is you move much faster if you're less wealthy first rather than healthier first, right? The inverse. So we actually don't always want to pick countries where one is healthier and the other one is wealthier, because now we have what's known as a confounding variable, right? That relationship, some other detail of that relationship might be the explanation for why one is moving faster than the other. So we want to try and hold the one variable constant, which is one of the two is healthier, and make sure the other variable, which is that the other country is wealthier, we want that to change. Sometimes we want the other country to be healthier, sometimes we want it to be less healthy to begin, and then we're kind of weeding out that confounding variable and focusing our hypothesis on this phenomenon. If the data supports that, then we might be able to lobby the government for a proposal, get some money, go visit some of these countries and actually see if we can uncover some of these detailed mechanisms and find the actual causal reasons. Okay, again, kind of a detailed example, but what we're doing is not passively looking at a picture or a video. We are actively interacting with it and reasoning about mechanism as we do so. Okay, we have 5 minutes left, so let's end with a little exercise here. Again, this is now kind of a historical document. I don't know if you remember the Netflix prize. This was a big deal about 10 years ago. Netflix posted a $1 million prize for anyone or any team that could come up with a machine learning algorithm that would predict when you watch a movie how many stars out of 5 you're going to give that movie before you assign your stars to that Netflix movie, right? So, not that different from what you're doing this week in Deliverable 4. We're creating, in this case, a machine learning algorithm that predicts, but it predicts a piece of information that is very, very important to Netflix. Why does Netflix want a machine learning algorithm that predicts your ratings? Who cares?
Because then they can recommend you movies that you're going to like.
They can recommend movies or make sure the next movie now starts immediately after the last show you were watching so you don't leave, right? Okay, so how did the prize work? They created almost 18,000 text files, and each individual text file corresponded to an individual movie. And inside any one of those files, which represented one movie, there were a number of rows, and each row had 3 numbers in it, which was the customer ID, the rating out of 5 that the customer gave to that movie, and the date on which they gave that rating. Okay? Some of these movies had more ratings in them than others. Here's an example of what you might find inside any one of these text files. They gave you these 18,000 text files. They gave you an additional text file which had the movie ID, the date the movie was released, and the name, the alphanumeric string of the name of the movie. That's your training set. Remember our discussion about the KNN algorithm last week, right? You take a training set, you do something with the training set, and then you're given a test set. You're given data for which the answers are hidden from you. And your machine learning algorithm has to produce the answer. Netflix looks at your answers, and they look at the actual answers, which you don't see, and whoever got the most answers right took home the $1 million. Okay, you've got 2 minutes, so turn to your neighbor and think about not the machine learning algorithm, but how would you start to visualize this data, to start to look for patterns in this data. Take 2 minutes to do that. I'll collect your attention back here, and we'll close up for today.
Tab watch just false. Recommend that. That's for the really basic one. You have one like it has more.
Okay, I realize you're just getting started. We'll continue with this next time. One last thing. You'll know this is a historical document because I had to explain at the top of the slide what Netflix was back at the beginning. You have a quiz due tonight. Please continue on with deliverable 4, and I will see you on Tuesday. Thank you.